and so binary neutron stars, and we have a lot of things to do. So I think with that, I would like to introduce our first speaker, who is the PI. Oh, and one thing, these workshops are supported, by the way, by NSF. All right, and I'd like to introduce Pablo Laguna for Georgia Tech, who is the PI of the NSF run that support this workshop.
Thank you. So do I get 10 more minutes as you take it early?
You can, we can get questions. Hopefully you're gonna.
All right. Perfect. All right. Good morning, and all right. All right. Good morning, and nice to be here. It's the first time that I'm in RIT. Beautiful campus. I bet the weather is like this all year round, right?
It could be worse.
All right. Yeah. So Manuela said, of course, most of the people here are the ones who are actually doing the work. I haven't hit the return key probably in 10 years or so, but I'm working with Manuel and others to keep this, the funding going of this project. So what I thought that it would be, all right. So what I thought that it would be interesting to do is I'm going to spend probably 10 minutes or so of telling you a little bit about the history of the Einstein Toolkit collaboration. The part about the funding mostly that led to some of the work. Then I will spend another 10 minutes or so telling you some of the results that we have obtained in Georgia Tech in the last 5 years or so, thanks to the use of the Einstein Toolkit. And I will end the talk telling you about the part in the development side that we have been working. All right. So it is amazing, but it's 12 years ago that we started the project. It was, at that time, I don't remember, what did we call it, Cyrel? I don't remember either.
It was an NEPS meeting, if you recall.
Yeah. But I looked at I have the proposal, I downloaded, and I couldn't tell why we call it Cyrel. But anyway, that was the beginning. In 2007, I think Carlos and you, Manuel, were still in Brownsville, right? I was back in Penn State, and you guys were in LSU. So then, after 3 years or so, we had this CIGAR. I think that acronym was you, Gav, the one who came up with it. Oh. And it was mostly motivated because we were going to go from this here mostly vacuum to doing general relativistic MHD. Then we renewed that one. And at the beginning of the Einstein Toolkit, if you read the proposal, it's available. It started here, but this is when officially we had the focus was the Einstein Toolkit. And then currently we are in the 1, 2, 3, 4. We're in the 4 renewal phase, and we're reaching the end. Next year will be the end. And this is the Einstein Toolkit for data integration and data exploration. And I put question marks because one of the things that we're going to do today, in the next couple of days, is get together and decide what to do next. And it has evolved. At the beginning, it was UT Brownsville, Penn State, and LSU. All the way now, we have Illinois, LSU, RFP, and Penn State with some other senior collaborators. So I'm just going to give you. I'm sorry.
The last proposal is actually on Zenodo. I think that we have it open if anyone wants to see what it is. I can't find the link right now.
Well, I mean, we can talk about it. I have the PDF of all of them, and I don't have anything I can put it in a website or something. I mean,
the last one is up there on the website.
All right, so this is, if you go to the proposal, the summary, this is for the first one, what we were focusing on. So it was adaptive mesh refinement. That's when I mentioned that it was the first time that there was some mention, at least in this proposal, the Einstein Toolkit. And as you will see, one of the themes that we included in most of the proposal was about data. It was not only about software development, but it was also about data. And we have different incarnations of this, as you will see, but I think that one of the important things that unfortunately I don't think we have developed as much as in the software side, but I think it's very, very important to do that. Okay, then the cigar, that was, as I mentioned, that you have the introduction of that we were going to have an effort in the GRMHT. There was, as most of you know, the Einstein Toolkit from the beginning had the hydro part, but it was from this collaboration in the EU. I don't recall that it had a specific name, but that's what that called the whiskey code, right? Start. And the idea is to expand it to GRMHT. And then it was an effort to enable new cyber infrastructure that involved not only I/O, but also visualization and so on. And here again, it was part about getting involved with complex computational environment. The Einstein Toolkit, as I call it, 1.0, it was more specific about these multi-clock structures. We still had issues about AMR scaling and accuracy that I think is still present today. And continue working the GRMHT. And here again, the theme was to get back into the data repository. The last one, continue here with the data simulation repository. And there were more specific things about the scheduler, initial data. I'll talk a little bit at the end. This was a very interesting. Is Eric here already or not? Eric Schmidt? Virtual is very. This is something that I remember he was very, very interested in that, to create some platforms, some tools to do experimentation and so on. The scheduler, I remember it was Steve Brand and at that time Frank Glover. I guess we're going to talk about what happened with that. That is something that. Here again, in the meeting that we had in Illinois, there were talks about this. I had to confess that I don't know where we are in that regard, but I think that's going to be part of the conversation today. All right, so that is what we have, and I think that it will be very important that not only the senior people get together to say, okay, where we want to go, but we get input from those who are developing and new ideas, and new people who want to be part of the collaboration. All right. Okay, so what I'm going to do now is just very few, 3 or 4 examples of things that were possible because we had this infrastructure. Okay? So the first one, that is a paper that has been recently submitted, Juan Calderon Bustillo is the lead on that. It's about the following. What he found, he's, as I call him, Mr. High Mode guru. He's the one who has been pushing this idea that if we include beyond the 2 mode in gravitational radiation, you can actually be able to get more information about the system. So what we have here in the top, okay, in the top here, you have a mass ratio Q equal 3, all right? And you have the chirp view from different directions. So here you have phase on, okay? And here you have in the direction of the, away from the kick, the final kick of the black hole, in the direction of the kick of the black hole, and some other direction, okay? And all of this is around the time in which the common horizon forms. And you can see that depending on that direction, this is the phase on, this is the characteristic thing that you have seen in most of the detections, you get the chirp. What is a chirp? For those students in the audience, is as a function of time. This is time going in the horizontal direction, and frequency. The frequency increases as time goes by. Not only that, the color gives you a sense of the intensity, so also the amplitude of the waveform increases. So what is interesting here is that you get these other 2 bumps. Here, you can see that they're very pronounced. Here is, again, the case in one of these, I don't remember which direction it is, but now, instead of looking at the same object from different directions. This is q equal 3. Then you have q equal 1.1, 2, 5, 6, and 10. So you can see that this double chirp, okay, as one likes to call it, is more pronounced the larger the mass ratio is. And the thing is that, as you will see in another paper that I'm going to show next, it is for large Qs, which unfortunately have not been the ones that are detected by LIGO yet. It is in the large Qs in which the presence of higher modes is more relevant, modes beyond 2 or 3. Okay, so what's happening here? Well, what's happening is something that is, when one showed me this, I could not believe it. It took a while. I was not getting the whole picture, but this is the picture that he came up to convince not only me but others that happened. So this is kick off. This is the direction away from the kick of the final black hole, and this is the direction in when you see the black hole coming towards you. And what he's plotting here is psi4, or maybe the strain, I don't remember. And what you can see here is that in this direction, if you cut across this direction here, you're going to see that you're going to get this front first. There is a little here, and then you're going to get another front here. Look, the color is the intensity. Away from it, you just see 1. Because by the time that this second front goes, it's just too weak. That's why you only see 1. So if you look that in terms of the time frequency map, this direction here, the kick on observing, is these two here, are those two fronts going by. So that's what it is. All right. So then how does this originate? And the way why he has imaging the black hole, which is something that's stretching it a little, but it's okay. One likes to take these flashy titles. And the way it is that if you go closer, here you already have a common horizon. If you go closer, there is a correlation between the shape of the horizon that it has a merger and these arms of radiation coming through that. And that correlation, that actually is not the first time that it was found. If some of you have read Luciano's paper, were you in that paper, the anti-kick? No? Okay. So Luciano had this beautiful explanation about how you get the anti-kick, and it was connected to the deformation of the horizon. So in this case, that deformation is a connection between these arms, so to speak, that eventually is a radiation that will read it. And Chris Evans, that is somewhere there in the back, he was the one who calculated quantities in the horizon and the curvature there in the horizon, and found that yes, indeed there is a correlation between the local curvature in the horizon and the gravitational radiation. All right, so this is one, and all this machinery comes from the Einstein Toolkit. Okay. Then another paper that is the second part of what we did when Jim Haley, where is the skinny guy? There. Jim Haley was a postdoc in Penn State and in Georgia Tech, and that's when we found this correlation between the frequency. So here you have the amplitude, okay, time here, the amplitude, and this is the maximum amplitude. Remember, the chirp is over here, it's increasing in amplitude. The frequency is also increasing. So what we did is, at the maximum of the signal, we read the frequency of the gravitational wave. Okay? So at the time in which the signal is maximum, we go and read the frequency. Then we found, Jim found, a correlation between those two quantities, I mean the frequency there, and the quasi-normal ringing. Okay? And also the decaying time. So, but let's just focus on the quasi-normal ringing. So what Deborah did, is a graduate student of Iran in Georgia Tech, she converted that mostly to a strain that is more natural for gravitational wave observations. And the other thing is, as you know, in numerical relativity, we have the gravitational waves in dimensionless units. Typically, we use the total mass of the binary for that. So what we were after here is there a way to know about the final black hole without having to use a template? That was the whole idea of this project. Can we use this information that is connecting the frequency at peak to know about the final spin and final mass of the black hole? Okay. In the work with Jim, we had everything in terms of the mass of the binary. How do you get the mass of the binary? You need a template, you need the spiral. So part of this recasting this result is that now we write it in terms of the shear mass, that you can calculate the shear mass without having to have a template. Okay? So the good thing is that in principle, you go and read the frequency here, you go to this table here, let's say that is at 1.17, you go here, go up, and then you know that your black hole has a spin of 0.7. The only number that you need to know besides this frequency here is to calculate the shear of the black hole. So what they did, what Deborah did together with James Clark, was to assume a signal-to-noise ratio of 100. Then they go and inject a signal, like the 150914-like signal, with 2,000 realizations of noise. So that is your data that you think the answer is giving. Okay? And then with that one, remember, we don't want to use waveforms. Waveforms, templates. So what we do is we use this base wave reconstruction that is typically used by the first group in LIGO that doesn't assume anything about the source, and compute the waveforms. Right? Now, from those waveforms, you go and read the frequency at peak and the time derivative of the frequency at peak. From those two quantities, because the time frequency enters here and there, from those two, then you calculate what is the probability of measuring that. So here in red is the true spin of the black hole, okay? And in black is the one that you get from reconstruction. So in principle, although the errors are quite large, these dash marks are a sense of the error, in principle, you can just by reading the frequency at peak, doing and the shear mass, you can say something about the final black hole. And again, all the tools used here are the Einstein tools, Toolkit tools. One another thing, and that is one of the very interesting things, is about kicks. From here, when we were at Penn State, we were looking at kicks from all sorts of directions and so on in the simulations. And what here again one said, well, can we use the waveforms? I mean, can we use the data that LIGO's collected to say something about the kicks? And and here again is Mr. Higher Mode. What he realized is that depending on the direction that you observe the binary, the modes that enter, the higher modes that enter, that they have entered to produce the kick, produce a different overlap. So for instance here, you have a Q 1.25 for this black hole. These are angles, let's forget about it right now by the mid. Here, the center is exactly edge on. So what he found is that there is a correlation. Q equals 3, as I mentioned before, is when the higher modes are more relevant. What he found is that he can distinguish the two scenarios and the direction of the kick. So what he needs to do is to first the inclination. LIGO does that. And if you go and look at the data, at the report for each of the binaries, it tells you about the inclination of the binary. The one that is connected to the kick is this azimuthal angle. But the azimuthal angle doesn't have much physical meaning. I mean, it's arbitrary. You can the inclination, yes, I mean, it's the inclination of the orbit, but where in the azimuthal angle things are, that doesn't have much physical meaning. So what one look is that if you pick what he calls the kick frame, that is, he went and aligned the system in the direction of the kick, then the azimuthal angle at least has some physical meaning relative to that kick direction. And with that one, he was able to to be able to read off the kick out of the gravitational wave. One more, okay? This is about detectability, the impact of precession on higher modes. So here are 4 examples from our catalog that was produced with the Einstein Toolkit. Here is a Q equal 10 with non-spinning black holes, Q 1.5 precessing, Q6 precessing and Q7 precessing. What I'm plotting here is time in the horizontal direction, and in the vertical direction, the amplitude of the strain. And solid line is in 2-2 mode, long dash is 2-1, and short dash is 3-3. So, and as you can see, precession brings the higher modes to be more relevant. Okay. These two cases with precession, as well as large Q. Large Q here doesn't help because the black holes don't have speed. All right. So here is another way to put it. It's the same simulation here, but now you can see here is the frequency. So you can see that now precession not only has those oscillations there, but also the higher modes are more relevant. And what he went and did, or what Juan did, was to calculate the fractional volume lost. So that is how much of the volume that you can observe for this type of SNR and this type of energy you're going to lose because you don't include the higher modes. So here is an example, okay? Here is an example in which you only use the 2-2 mode. You only use the 2-2 mode. Here is 10%, okay? You only use 2-2 mode. These are a series of simulations and so on. But you can see that you're going to be able to miss this here. That are if you don't include that. Here, okay, if you have not phase on, here you're taking advantage that phase on, the 2-2 mode has most of the information. But if you don't use the 2-2, if you don't have that is not phase on, higher modes contribute, and you can see that there are more cases that are above 10% for which you will be losing volume for the patch. All right. Last, okay. This was 3 years ago, something with former graduate student Michael Clark. So we were trying to, as you know, there will be conversations here about that. Initial data continues to be a challenge now, especially for neutron stars. We got the Lorraine, I think there's a couple of talks on that, or a talk on that. So what I was interested in is to see, is there method as simple as the one that we use with Bowen Yorks and punctures to be able to include the neutron star. So we don't claim that this is the best method, but this is very fast in the following sense. So I'm going to be a little technical here. The Bowen and York solution for the momentum constraint for point particles are these two expressions. This is for linear momentum, and this is for spin. Jim York and Bowen came up with this solution. So what we do is we pick this solution, plug it into the Hamiltonian constraint, a single equation. We use the two punctures, and there you have it. Okay. So it turns out that Bowen and York also wrote solutions for the extrinsic curvature, for linear momentum, and with the spin for spherical symmetric sources. The way that you specify the sources is through these functions. I didn't bother putting how you do it, but it's f, h, and that's it. Okay? All right? And you can show that if you put here, for these functions, the one that corresponds to a point particle, this one reduces to that, and this one reduces to that. This is a little bit simpler to see. The end, it just becomes 1. Okay? All right. And those are just integrals of some source distribution. Unfortunately, it's spherical. Yes, you're going to criticize that you don't have the tidal effects and blah, blah, blah. But if you're sufficiently far away and so on, I think you can actually get a little bit of insight there. It's not perfect data, but the claim is that it's very fast to do. And in that paper, we did a double neutron star black hole, and neutron star with binary. So this is it. And yes, you get some spurious oscillations, but I think you also get them in the other methods. We're currently working in ways to control that. I think we have found ways to do that, and to be able to refine a little bit more this method. So in terms of the initial data, that was part of what we were doing in this incarnation of the proposal of the grant. We have focused on this. In adding sources, but also you have seen that there is an interest for alternative theories of gravity. especially scalar tensor theories of gravity. So we have initial data with scalars, got initial data with Maxwell fields, and so on. So to summarize, I think that it is important that this community continues working on the Einstein Toolkit, whatever phase or whatever evolution it takes. And it is important to be open. And I think we're going to do our best to be able to continue the funding that will support. It's a modest amount, but it still is an amount that allows us to have meetings like this and to support few students in that. Thank you.